Welcome back to Peking University MOOC Bioinformatics Introduction and Methods. I am Ge Gao from the Center for Bioinformatics, Peking University. Let's continue this week's topic, Markov model. Last time we introduced the concept of Markov chain. With the concept of state, we can distinguish between opening and extending a gap, and applying a fine gap penalty correctly. It is obvious, however, that these are not enough for real sequence alignment in practice. The current state model discriminates only between gap state X or Y and match state M, but not between different residues. Therefore, we need to introduce the hidden Markov model. The hidden Markov model adds to the states in Markov model the concept of tokens. Each state can emit a state of observable tokens with different probabilities. In other words, aside from the transition probability, the hidden Markov model has also introduced the concept of emission probability. Each state has its own emission probability distribution, which generates a set of observable tokens with different probabilities. In contrast to Markov model, the state path is not immediately visible in hidden Markov model. That's why it's hidden Markov model. Rather, we need to deduce the state path by the corresponding tokens observed. For example, the string AABC can have its state path being 1, 1, 2, 3, 1, 2, 3, 3, 1, 3, 3, 3, 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, etc. This is because each state is able to emit A, B, and C. The problem is that the emission probability for A, B, and C are different between different states. Thus, through different state paths, we will get different emission probabilities for string AABC. Theoretically, we can enumerate all possibility state paths right. Then we can calculate a probability for each path right. The one whose probability is maximum is the most likely path. For example, the probability of emitting the string AABC from the state path 1, 2, 3, 3 is the probability of emitting A from state 1, which is 0.8, multiplied by the probability of transiting from state 1 to state 2, which is 0.3, multiplied by the probability of emitting A from state 2, which is 0.2, multiplied by the probability of transiting from state 2 to state 3, which is 0.5, multiplied by the probability of transiting from state 3 to state 3 itself, which is 1, multiplied by the probability of emitting C from state 3, which is 0.1, which ends up with 0.00072. Actually, in this way, we can compute the probability of generating the string AABC for any given state path. The state path whose probability is the largest will thus be the path most likely to generate this string. For convenience, we will define the emission probability, denotes as EKB, as the probability of emitting token B at the state Sk. Then we can use the multiplication theorem on probability to rewrite the probability of generating tokens string Y from state path X as a production of the emission probability EKB and the transition probability alpha KL. Now that we have introduced the hidden Markov model, let's come back to the sequence alignment problem with a fine gap penalty. As discussed earlier, the Markov chain model can distinguish between opening and extending a gap by introducing the gap states X, Y, and match state M. However, it does not consider the difference between residues. Therefore, we will now take this into account using hidden Markov model. Specifically, we will use the emission probability to handle the differences between residues. The tokens generated from state M are all possible substitutions of residues. The corresponding emission probability is PAB. The tokens generated from state X and Y are all possible insertions of residues. The corresponding emission probability is QA. In this way, we can simultaneously deal with states and the specific residues easily. The sequence alignment problem can thus be reformulated as a problem where we need to find the state paths that most likely to generate the given token string under the given hidden Markov model. Specifically, we can use the idea of dynamic programming to solve it step by step. We define PMIJ as the largest probability that can be generated from the alignment of the subsequence of sequence X from the first base to the ith base, and the subsequence of sequence Y from the first base to the jth base, given Xi aligned to Yj. We also define Pxij or Pyij as the largest probability that can be generated from the alignment of subsequence of sequence X from the first base to the ith base, and the subsequence of the sequence Y from the first base to the jth base, given Xi or Yj aligned to a gap. Thus, we can define the recursive function at each step based on the state diagram. The final alignment can also be recovered by the backtracking method in dynamic programming. Let's summarize. In this unit, we have introduced the hidden Markov model and used it to solve the sequence alignment problem with a fine gap penalty. Students who have watched the supplementary learning material may have a question now. As we have already solved sequence alignment in week 2 by simply introducing states M, X, and Y, why still taking the time and effort to spend 2 units introducing the hidden Markov model and other various new concepts? How could they still benefit us if we have already had the old good method? First, the introduction of hidden Markov model gives a probabilistic interpretation of sequence alignment. For example, the delta here can be regarded as a probability of developing a DNA insertion or deletion during the evolutionary process. In other words, the delta can also be regarded as a probability of developing an insertion or deletion during the evolutionary process. Another example is that the emission probabilities of state M correspond straightforward to the frequency of various substitutions during the evolutionary process. Also, with a probabilistic model, we can leverage the probability theory to do more analysis. For example, we can compute the identity that is most likely for 2 given sequences to have, even without generating any alignment. In fact, we have mentioned at the beginning of this unit that the same sequence observed can come from many different state paths in HMM. Therefore, we can get the full probability for the observed sequence by summing up the probabilities for generating such a sequence over all possible state paths. In the sense of sequence alignment itself, this full probability is the sum of the probabilities over all possible alignments, or in other words, the identity that is most likely for 2 given sequences to have. In practice, it is very simple to calculate. In fact, we only need to replace the maximum function with summation at each recursion step and the final step. This method does not depend on specific alignments, which is especially important to cases mentioned before while multiple optimal alignments exist. Last but not least, we will discuss about the feature of deducing hidden states from observed token sequences in hidden Markov model. In fact, hidden Markov model is used more as a predictor in modern bioinformatics research. We will introduce this in next unit. Here are some summary questions. You are encouraged to think about them and discuss them with other students and TAs in the forum. Thank you. Let's meet at the next unit.